different predictor variables. Okay, so that is what we are trying to predict. This is a regression problem, and the area, the variable of interest is the house price, specifically the median value of the house price of that particular state. Okay, that is what we are trying to predict. Any questions regarding this?
The data set.
Okay.
What I suggest, right? If you can show us the that data set, right? So what is the input, right? So the input versus output. So that will be good to the team, right? So if
I understand. I understand. So I am getting to that. I am just beginning my code. I am getting to that. It is there. As we proceed, it will be shown. It's there. It's there. So we can definitely visit the data set. I'll show. It's there. Let me continue. So these are just okay. Now this is the step. This is where we are loading the data set. Now since it comes pre-packaged with sklearn, so I'm not going to import it from the internet. Rather, it's there. It comes as a bundle data set. So first, okay. So now we are going to check the various attributes. All right. So let me just quickly execute this line of code. So what we see here is the entire information related to the data set. Okay, so what do we see here? This particular line, say shape. So it tells us that the data set comprises 506 the houses. There are 506 houses, and there are 13 different variables for every house. And these are those variables. Okay, and if you want a description of these variables, it's mentioned here. Okay, right? These are the descriptions. And this particular variable MEDV, this is the variable that we are trying to predict. So this is actually price of the house in thousands of dollars. So if you say it appears as 10, it means $10,000, and so on and so forth. All right. So this is the data that we are working with. And if you want a better explanation, or rather you want a better visualization, we can also do that. Moving on. All right. So let me quickly break this into two parts so that it becomes easier.
No. 2 minutes.
See. So now this is the data frame now. All right. So what we are doing is bringing it into structure. So what happens is when we import data which are pre-packaged, which are bundled with scikit-learn, they do not come in the form of data frame. Rather, they are in the form of dictionaries, as we see here. All right. And dictionaries contain information about the data, the names of the variable, the description, and the target. But we don't want it in this format. Rather, we want it in the format which we are able to analyze, something in the form of an Excel file. Imagine this is an Excel file, and these are the columns 0, 1, 2, 3, 4. These are all columns. All right. But then 0, 1, 2, 3, 4 are again not very intuitive. So what we should do is we should convert them to the appropriate names. Hence, this step here is what we are trying to convert. So we are converting the names to the actual names of how they are. So here we see this is no different from what is here. It's simply that the mapping of the names have been done. So the variables have been mapped appropriately. And then if you now observe in the data here, we just have 13 features, but we do not have the target here. Target here is the median value of the owner occupied homes. So that happens to be our target. Okay. So now what we need to do is we need to append this information here. All right. To append this information here, we have to first do some kind of transformation. So what you're doing is we are adding it as a variable of this data set or this data frame. Okay. So we are adding it by under this name MEDV, and then we're doing a head. Head is just to show the first 5 rows. Okay. So this is our data frame, this one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 predictors and 1 target. Okay. So this is our data. This is what we'll be working with. Okay. Any questions so far? All right. So we can move on to the next step.
Prudhu, I have a question, Prudhu. Prudhu, how are, see this median WDVE, right? So
Right.
is it you're predicting it, or else you're directly, see, from the, see, how does MDV comes to me, right? For example, I'm asking, right? See, these 12 values you're putting, the 13th value, right? You're directly populating from the, like the pre-structured data or predefined data to this, or how this MDV values are populated?
All right, all right, all right. So there is this notion of training some data, okay? Oh, sorry, training some model based on historical data. Okay, the key word here is historical. Hence, we use data points which are already there. Okay, so we use information which is already there with us. Using that information, we try to create a model. Now, that model, what it will do is, it will not, let's say you want to use it on future data points, which meaning you do not have the information about MEDV for some other data points. So here we have just 506 data points. Let me just go back to the, see, we just have 506 houses, right? Now we'll feed the information about these 506 houses along with the actual target, meaning this MEDV is already existing because it is in the past. So we already know about the value. But what we are going to do is we are going to create a formula or create a function which is going to predict the target for some other value which is not amongst these 506. Okay. So the idea is to generate a set of rules which can be generalized. You know, devise a set of rules which can be generalized to any house which carries these characteristics, all right, or these variables. So if, let's say for instance, let's say highly speaking, we have a model which you devise using this formula or this regression, and based upon such variables, let's say for instance we have some house in India itself, let's say, and these are the variables or these are the pieces of information till else that if we are provided with such information for that particular house, applying this particular model, or which you're going to show later on, that will be able to tell us what is the most likely median value of that particular house. Okay, so right now as we speak, these values which we are going to observe are already present. But having said that, we not only create a value or the predicted value from these, but we also try to prove that our prediction for something which is beyond this data, okay, any point which is not within this data, that we will predict or we shall showcase to somebody, our claim should be as close to reality as possible. That is what we are trying to achieve. Okay, I hope that is clear in some sense. So it will be clearer, it will become clearer once we move ahead. All right, so now for instance, okay, so we have reached this particular step. So since all of these information is in numeric form, so we can in the statistical jargon we can do a 5-point statistic, or in this case particular says a 6-point statistic. So we have the actual mean, the standard deviation, minimum, first quartile, median, third quartile, and the maximum value. All right, so this is called a 5-point statistic in addition with the mean. Right? And of course we have the counts. So we don't see any missing values here. Obviously, this data set has been taken from UCI website. So they have already done all their due diligence by creating, probably they have imputed values. So I'm not very aware of that. But now this particular step that we are viewing right now is the first of the most crucial steps. You know, like you asked me, what is it that we're trying to predict, or is the information already there, or is it something which we are going to forecast? Now this is where we are trying to simulate what exactly prediction means. So this is what you're trying to simulate. So imagine just to put some perspective, imagine you have an Excel file. Okay, Excel file which has 506 rows. Okay, so from that Excel file we're going to create two smaller Excel files or two subsets of Excel files. Now the subsets will be divided in this format. You see this test size 0.33, it is nothing but 1/3. So 2/3 of 506. That is, let me just quickly calculate it for you. What is 2/3? So 506 times 2 divided by 3. Okay, 337. So 337 rows from that Excel file would be left aside, or rather would be taken as the training data. The word that we use here is training data, and the remaining would be used for testing. Okay, so when we say testing, at once we are trying to simulate the real world scenario, which means we are trying to say that for the testing data, we do not know what is the target, what is the value of the target. We do not know. That's what we are trying to simulate. Hence, by using the training data and training a model and getting a set of getting a function with a set of rules, we try to predict the target for the test data. So that is how this is the exact framework of predictive analytics. So you take the total information, you break it up into train and test, you build your model, you fit your model to the train, and then you try to predict what is it going to be like on some unseen data. In this particular case, the unseen data happens to be test data. Okay, so this is what we actually do in predictive analytics. This is standard framework. So here what we are doing is we are breaking it up into 2/3 and 1/3. So 2/3 of the data would be held out, 1/3 of the data would be held out for testing, and the remaining would be for training. Okay. So at once we see 339. Okay, 339 and 13 columns. This comprises the training set. 167 and 13 comprises the test set. And what we see here, this is nothing but the this is nothing but the target variable for the train set. This is the target variable for the test set. However, we are not going to do anything with this other than comparison. So this is the actual value which we have in the test, but what we are going to do is we are going to use only this information, that is 167 and 13, to predict 167 new values. Now those new values, those new 167 values would be compared against the test so as to check the accuracy. That's all. Okay. And so then the next step is,
Sorry, I have a question here. Why are you taking 67, right? I can take 80, I can take 90, and so why so is there any benchmark you saying that, hey,
there is no benchmark. The only rule of thumb is the more data you use for training, the better estimates you may expect. Now again, I'm using the term you may, because some algorithms do very well with say 50-50. They do very well. Whereas in some cases, say regression, in regression, the more data you provide, the better it becomes, the better the yield, the estimates would be. All right. So there is no hard and fast rule. But then, since we do not have much data, we just have 506 data points. Okay. So that's why I just took, in this particular case, 2/3. We can very well, let's say if it had millions of data points, we could have taken 50% sample. No big deal. Okay. So there is no hard and fast rule.
For example, I am saying that there is 1 million records, 10 million records, or like 150 million records. So is there any thumb rule I should go for? Like in that case, right? I should say, right? Oh, okay, 70-30 or 50-50 or 80-20. So see, what is the benchmark? So you are saying, okay, I have a less record, so I went to this. So is there any rule I have to go and say, hey, okay, based on the volume of the data, I take 80%. Oh, okay, it is less volume, I take 70. What is that? Anything like that?
No, it is actually more about practice. See, what happens is when you start off, at the beginning, I used to take 90%, 90-10. Okay, but later on I realized there is no need to take the entirety of the data, because if you are using the correct features or say correct columns or variables for prediction, the information may be captured. In some cases, for instance, let me quote something which is very advanced. So you might have learned or you might have heard about deep learning algorithms, which is nothing but multi-level neural networks, right? So in deep learning algo, you don't even need a test. You can take the whole of the data and just be rest assured that it is going to give out very correct or very, very accurate results. Why? Because whatever new data or whatever data which comes in, the results, the forecast results which you get or the predicted results which you get is as close to reality as possible. It has been proved. Okay, so that is one of the way of taking it. In other way, let's say if you're somebody who's beginning with analytics, so I would definitely suggest take more of the data for training. Take more of the data. I'm not saying take how much, I'm saying more. So again, more could be 5149, but then obviously it all depends again on what kind of regression or what kind of technique you're using. In some cases, for say in decision trees or in say random forests, so you might want to take say around 70 to 80% of data. But then again, there is no rule of thumb here because it is more about practice. So more you practice, the better idea you will have. So this is not a what do you say? There is no clear-cut guideline. There is no principle. It is more about understanding how well your fit is. If your fit is good with 50%, you might as well have 50%. And in some cases, we also do a three split. That is, you have a train, you have a validation, and you have a split. Test. So you have the entire data. So you take train, validation, and test. So what you do is you leave out test. You don't even touch it. Okay. You take the train, you do whatever model fitting which you do on the train. Then you check how well does it fit on the validation. But then once you are not satisfied, you again come back to the train. You do some different sort of feature tuning. You create more variables. Okay. And then again you test on your validation. This time around, you feel that, okay, the results are slightly satisfactory as compared to the earlier iteration. Hence, you again, now this time, you move ahead to the test and then you again predict. Okay. And then that's how the entire practice is. So if you say that what is the ideal way of going ahead, it is actually to split into three parts. That is a train, a validation, and a test. But again, here, since for want of more data points, I have just taken two splits. That is a train and a.
Can you give an example for this validation, right? Because I understand it's 70th, like I know, right? This one you got. So if it is a validation, how do you divide it?
Okay, so in this case, I am using inbuilt function here. Okay, so there is no inbuilt function for validation. So imagine again, this is how to do it. So you have np.random. Okay, that is a way of creating random numbers in Python. So what you can do is you can assign. Okay, I hope people understand Python here. So what you can generate is random numbers of, let's say, 100 data points. So you divide into three parts. All right. So 40, 30, 30. Okay. So 40 data points randomly chosen from 1 to 100. You leave as training. The remaining 60 out of that, take any random 30 as your validation, and the last 30 would be test. Are you able to follow what I'm saying?
Yeah,
is this clear?
You carry on, no problem. Yeah, let's carry on.
Yeah.
So one question though. So the reason why you are splitting the data is because you have the same data for creating the model and to validate and to test. So that's why you have to split the data.
Correct. So you do not want to train as well as test on the exact data point. That you would not want to do. You would obviously want to train on X data point, test on some other X data points. Correct? Only then somebody can bank on your prediction. Otherwise, if you simply train and test on the very same data point, you will just being very optimistic with the results.
Yeah, it will obviously work because you have the full data set, you have already used it. So it will anyway pass the test.
Sorry?
If you use all the data and create a model, it will anyway pass the test because it will be a subset anyway.
Correct. So now that will only give you optimistic results.
Yeah.
But then it is not a realistic result.
Absolutely.
To get a realistic result, you should have something which you have not seen. Now, how do you simulate that? To simulate that, you have to break it up into parts, which is nothing but train, validation, split, and test. Okay.
Yeah. And once you test it, then you prove the test. you can extrapolate to real life scenario.
Yeah, so once you have finalized, you have locked your formula, you locked your model, then you do not touch it. Then whatever new data points come, you simply use those data points and you generate your forecast values or predicted values. Okay.
Yeah, got it. Thank you.
Okay. And again, so in this section here, we see we simply train the model. We are using linear regression. And just to tell you a few things here, how many variables did you use? We used all of the variables. We used all of these, starting from CRIM to LSTAT. All of them have been used in the model. Okay, here. So you are fitting. Okay, this is in scikit-learn. So you initialize. I hope people who understand object oriented. This is nothing but the constructor. So you instantiate an object of type LM, of type linear regression. You name it as LM. You fit, that is the x's and the target. We know x is 339 rows, 13 columns. Target is 339 rows, 1 column. Okay, and then you try to predict. Predict is always on the test, which is you use this information, 167 rows and 13 columns, meaning these columns, and you try to predict your values here. You try to predict your values here, which would then be compared against the actual values. Okay. Now this is the plot. Now again, what is this plot? Imagine, ideally, if our predictions would have been perfect. Okay, absolutely perfect. Okay, can somebody answer what kind of plot this would have been? Can somebody answer?
It should be linear, right?
Linear, yes, but specifically, what kind of a specific plot? What kind of a specific linear plot should it be? Specifically.
Maybe straight line?
Yes, it would be a perfect straight line of 45 degrees. Okay.
Okay.
I hope now things are clearer.
No,
a bit clearer.
I guessed it. As I told you, right? How do you get? I don't know, but I guessed it.
Yeah. So imagine. So okay, it's very straightforward. Imagine you have predicted median value as 10. Okay, predicted as 10. All right, and the actual value also happens to be 10. So you will only plot here, right, at this point. Similarly, if you have predicted 20, and the actual value happens to be 20, you will only get a point here. You won't get any point anywhere else apart from these, this diagonal starting at the origin and extending to infinity with a slope of 1, that is 1045. Correct? So that is how. So now what we see here, we see that it is not exactly a straight line, but then we do see a linear relationship. So imagine if you just were to draw an imaginary line through this, it is more or less telling you, yes, most of the information is being captured. By information, I mean whatever is our prediction, it is in line with what the real, what the ground truth is. Okay, so that is what this particular line denotes. Imagine if this would have been a really, really bad fit, then you would have got data points all over. So you would not have seen any pattern. You'd have seen data points scattered all over. No pattern as such. Okay. And now these are things. Yeah, please.
So if you have an outlier, so how will you address that? If you have 2-3 outlier points.
Okay, first of all, okay, do you know what exactly is an outlier? What is the notion of an outlier?
Yeah, I mean, I know basically it doesn't fit the standard, there will be beyond standard deviation.
Okay, so it is like this. So outlier analysis is something which we do prior to the building of the model. And taking your question, that is, what happens if there are outliers? For that, we'll have to check if at all there is any outlier. Okay, so for that purpose, we'll have to plot. We'll have to create plots of, in this case, let's say we'll create pairwise plots of all of these variables with respect to this variable. Okay, and then we'll see if there are points which are very extreme. So outlier could be somewhere, okay, forget this plot. Don't assume that I'm trying to show outliers here. Assuming that one of the axis is MEDV, which is our target, and the other axis is one of the predictor variables. Okay. So then if you happen to see outliers, you will see them, not with the general data points, you will see them apart from each other. But it is, again, we do not call them outliers. We say they are potential outliers. They may or may not be. Why? Because when we see pairwise, they may appear as outliers, because we can only, at the most, we can visualize 3D. We cannot visualize more than 3D. Correct?
Yeah. Yeah.
Correct. So imagine if you have to do it in a 3-dimensional figure. So you will have at the most three different axes. One of them is the target, obviously, and the other two are the predictors. And you see a point which is slightly far off.
Yeah.
But having said that, what is the technique you are using is also going to govern whether outlier analysis is required or not. For instance, regression is extremely susceptible to outliers, meaning your regression coefficient, your regression estimate will go off. It will go off track if there are outliers. So you will have to handle them. Okay. So what are the ways of handling? There are ways of handling outliers. Obviously, if I were to go and explain that in this at this point of time, it will eat into our session. But if you want, we can discuss.
Yeah, I'll ping you later. Yeah, thanks, Pratik.
Yeah, but then just the takeaway is we have to first treat the outliers. Now, how do we treat them? There are ways. There is something called as flooring, capping, removal altogether, or let's say you have 100 data points, of which 30 seem to be outliers. So what you do is you create two different models. One for those 100, one for the 70 data points, and one separate model, especially for those data points which you feel should be part of a different analysis altogether. So you cannot analyze both the data points, both these types of data points together. It makes more sense to have them separately. For instance, imagine you are trying to analyze prices of vehicles, all right? So in vehicles, you have various types of variants. So you have luxury, you have economy, and so on and so forth. And some of them which are there are on demand. Some of the car manufacturers, they manufacture only on demand. So those kind of vehicles, if you want to analyze, you will not be clubbing them with your ordinary, say, everyday car manufacturers. Rather, you will treat them as a special category. So
Right.
those vehicles, you will do a different analysis altogether, keeping only vehicles of such type together and then analyzing. You get it? You just try to
Yeah. So you do conditional modelings and you apply what model is applicable to which data set?
Conditional modeling, I don't know what is conditional modeling.
There's no term like that. I'm just saying that you create two different models and apply as applicable.
No, not that way. Not that way. No, you don't create two different models. Again, you check your data. You feel that a model, it is not like one size fits all. Say one size fits all does not work. Then you will segregate your data. Okay, and then you create one fit for a different set of data points which you feel when they are taken together, when they are considered together, it makes more sense to have a common model. And similarly for the other one. So it does not make sense to have them in one space and trying to build a model. Okay, when you feel that such a thing is not very intuitive, doesn't make much of a sense, then you differentiate, or you draw a line, you bifurcate them, or maybe create many different proper subsets, and then you create different models. Okay.
Right. Yeah, thanks.
All right. The layman guys, right? See, I know they're talking about the outlier. So in general, right, to a layman to understand, right, if you want to explain layman in a simple terms, right, what is an outlier?
Yeah. Okay, you want me to answer?
No, yeah, I want you to answer. Very simple, right? I don't want to, I know you have explained.
Okay. What is an outlier? Say an outlier, okay, actually I should not use the term outlier. I use the term called leverage points, because, when we say outlier in this particular context, outlier is only with respect to the response, and leverage points are with respect to the predictors. Okay. So you might want to make a note of this term, leverage points. So what happens is, let's say you have your data. When I say data, I'm talking about one record, one row, one particular row. For instance, look at this line. This is one row, right? 24 is the price of this house, which has these features, 4.98 for LSTAT. All right, these are the features of this particular house. This is one house, one rent. Imagine you had a median value which is say around 100. Okay, now let's do. I think it will be very simple to follow here. Let's say, or rather, you have it here itself. It's described here. All right. So what is the minimum value here? 5. You see 5. What is the maximum value? 50. Correct. So now let's see if you had a data point which was 500 here. Okay. So the maximum value is 500. Now, in close inspection, you see that yes, it does not fit in this particular data. Rather, it is maybe, okay, hypothetically speaking, it could be the White House for all we know, because this is in the US, right? Again, this is just to give an example. So then at once you realize that, okay, it is very, very far off. It doesn't make sense to have it as part of this particular analysis. So you will earmark that record as, okay, this is not suitable for a model. Rather, this should be treated differently. You understand? This is the intuition here. I hope people understood this point.
Carry on.
Yeah. All right. So, okay. So after having built the model, again here, this is something which would be discussing in today's session. But again, this is just to tell you how well does your model fit. How well does your model fit? Okay. So these are the diagnostics. I'm sure some of you might know what these values mean, but again, for the benefit of the uninitiated, let me just tell you. So these are the p values associated with each of the estimates. All right. Again, I'll come back to all of it when we have our session. I mean, this is just a introductory thing just to set the context. So these are the variables which we have used in as the predictors, right? This is the intercept, right? This is the intercept, which is nothing but the line which cuts the y-axis in this case. So, this is the predicted value of y, right? And what are the coefficient estimates? So these are the coefficient estimates that you see. LM_coef is this one. These are the coefficient estimates. Some of the variables you see, CRIM is a negative value. It has negative effect on the median price. ZN has a positive value on the median price. Okay. And then we also talk about the associated p values, which we'll talk about when we discuss the slide. So that is more to do with the significance. How significant is the estimate? It is denoted by the p value. And finally, what is the R square? That is the coefficient of determination. So how much of the model is being explained by how much of the data is being explained by the model is defined by something called as R square, which spans from 0 to 1. Okay. The closer it is to 1, the better it is. So this is R square. And finally, we check the accuracy of the model. In this case, we are using mean squared error, which is the difference between the actual value and the predicted value squared. So that is what it is. So this was the this one.
Pradeep, right? See, yeah. Because we are this session, right, will end in another 30 seconds. So what I was trying to the team, right, we'll have another 20 minutes of session, right? Maybe, right? Okay. Because as scheduled, right, we'll be having 1 hour kind of a thing. But because of this particular scheduled event, like only takes you for 40 minutes, so it will kick me out, and then you have to rejoin it. So we'll rejoin again. So it will be again 20 minutes. I think, right, within 20 minutes we'll conclude, and then maybe right, whatever it is pending or pending, we'll take it to the next class. Sure. So give me 2 minutes. I'll just go have some water and then. Yeah, absolutely. I'll log in again. So I think the team can.